In this example, we'll look at a method that's a little bit different than what we've seen in the other examples. And we notice, first of all, that neither of the methods that we mapped out previously would apply here. For instance, we don't have an even power of secant, and we don't have a secant x and a tangent x that we could say for substituting if we wanted to substitute secant. So instead what we could do is something maybe a little bit more similar to the case when we had an odd power of sine or cosine, where I'll split up the cube here and write it as tan squared x times tan x. And after doing that, I notice that we can use an identity here to rewrite tan squared as secant squared minus 1. Now, when I look at this, what I notice is that secant squared is a derivative of tangent. So we could actually do a substitution if I distribute the tangent into the parentheses here. And what we obtain now is two terms, one of which we could do directly. For instance, I could directly integrate tan x. We know the antiderivative for that one already. And then secant squared times tangent, we can do a substitution, because when I substitute tangent, the derivative is secant squared. So let's start by splitting them up. If we recall here, the antiderivative for tan x was natural log of secant. Okay. And for this one, we're going to do a substitution with tangent. So before we rewrite the integral, let's let u equal to tan x. So du is secant squared. So our integral becomes u du. And now integrating that, we have 1/2 u squared, which then we substitute the tan x back in for u. And there we have it. So we'll bring down the natural log. For the final results. In this example, we're going to employ another tricky strategy. Again, we notice it doesn't have an even power of secant, so the strategy that we mapped out earlier wouldn't really work here. But what we could try here is something a little different. I notice, for instance, that if I were to split up the secant cubed as secant squared times secant, well, maybe we could try a slightly different approach. For instance, we can think about doing parts here. And the way I would think to do parts is using secant x as my u and secant squared as my dv. And this choice mostly is because we have an easy antiderivative for secant squared. We know that the antiderivative of secant squared is tangent. So let's do parts here, where I let u equal to secant x, and I let dv equal to secant squared. So then the derivative of secant is secant x tangent x, and the antiderivative of secant squared would be tangent x. So when we do parts, we'll have u times v is secant x tangent x minus the integral of v times du, so that would be tan x times secant x tangent x. So here I'll do secant x tangent x would give me another power of tangent there. And then looking at what we have here, I noticed that we can do a trick that we did in the last one where tan squared here can be rewritten as secant squared minus 1. So now my integral there will look like, now if I distribute secant, it will look like it contains the secant cubed, which is the same integral that we started with. So maybe that trick that we did earlier would also apply here. So distributing secant x into the parentheses, we get secant cubed minus secant. Now I'm going to distribute the integral to each term, so that way we can look at them separately here. So we'll have minus the integral of secant cubed, and then also minus negative secant x, so plus the integral of secant x. And if you recall, we had a formula for the derivative of, or the antiderivative of secant x. This was ln absolute value of secant x plus tangent x. Now, the one last piece that we have to do here is isolate the secant in the equation. So if I bring this back to the original, right, remember this is originally equal to the integral of secant cubed. So we can do that trick now by isolating the integral of secant cubed to both sides, adding integral of secant cubed to both sides. We can try and isolate it. So, for instance, over here, now this becomes 2 times the integral of secant cubed. And then what we're left with over here, we're left with secant x tangent x plus ln absolute value of secant x plus tangent x. And then finally, dividing the two, we get our integral of secant cubed. Is 1/2 secant x tangent x plus 1/2 ln absolute value of secant x plus tangent x. Okay. So that one's tricky, but you can see it utilized a couple of techniques that we've seen already. For instance, the first thing that we did was we split up the integral so that we could separate these two factors. And then we did integration by parts using the dv as secant squared and the u as secant x. And once we did that, then we were able to write the tan squared as secant squared minus 1, and distributing the secant into the parentheses, we could then isolate the secant cubed integral on one side of the equation and solve for it algebraically, giving us the result. Okay, so again, this is a little bit tricky to think of this as something to figure out without knowing the basic process, but with a little trial and error, usually you can stumble upon the right technique. And then one last set of formulas we want to look at are the product to sum formulas. So these are trig identities that allow us to rewrite a product in the form sine A cosine B, or in the form sine A sine B, or in the form cosine A cosine B. And in each case we're rewriting it as a sum of two trig functions as opposed to product. Okay, and so this is going to be helpful because on the right hand side we notice that when we're integrating, it's simpler to integrate a sum because you can then integrate each term individually. Whereas when you have a product, you can't do that. So let's try that here with this example. If I've got sine of 4x times cosine of 5x. So here I'm going to use this first product sum formula. So if I've got sine of 4x cosine of 5x, it's like my A is 4x and my B is 5x. So it'll become 1/2 sine of A minus B, that'll be 4x minus 5x. So negative x, plus sine of A plus B, so that'll be 4x plus 5x, which will be 9x. And now I can just integrate each term separately. So the integral of sine x will be negative cosine x, and then here dividing the negative 1 that we have there, so it'll be positive cosine x. Sine of 9x will be negative sine of 9x, or sorry, negative sine of cosine x over 9. Plus c. Okay. Actually, you notice here that it changed from negative x to x, and that's using the odd property of sine. So if I just take the negative out, then yeah, sine of negative x is equal to negative sine of x. So when I take the derivative, it's just negative negative cosine x.